Hi kids, Mr. Dorfler back at again. And before you even say anything, you might be wondering, isn't that the same shirt from the previous video? And you would be correct. I'm doing a lot of videos today, so there's always that possibility that you might see me wearing some very similar attire between videos. But, oh well, it's clean. Anyway, continuing our discussion in chapter 3. This is going to be a shorter discussion than the previous one. I told you the section 1 is going to be somewhat long. But in section 2, we're talking about reaction types. And the reason why it's important to know about reaction types is because we can take a look at a chemical equation and identify what's happening in the reaction itself. And it also gives us some insight into what products should be expected depending on the type of reaction that we have. Okay, and there's gonna be about 3 in this part. There's gonna be 3 main types we talk about. Now there are other ones that are gonna be in a different chapter. We'll deal with those later. Okay, but right now we're dealing with 3 main ones. The first one is called a combination reaction. And I'm going to move my face down just a little bit. All right, so in combination reaction, you can guess what is happening here. This is where we have 2 or more substances that are the reactants that combine together, and they react and combine together to form one product. So we have multiple reactants coming together to form one product. For example, looking down here, we have magnesium reacting with oxygen. Again, remember, oxygen is by itself. It has a subscript of 2 because it's a Brinkelhoff. They react together to form magnesium oxide. Now, that is a ionic compound, so we have to follow the ionic compound formula writing rules. You have to say that slowly, otherwise it's a tongue twister. Second example, where we have nitrogen, again, another Brinkelhoff, as you see with the subscript of 2, reacting with hydrogen, also a subscript of 2, also a Brinkelhoff, coming together to form NH3 as their product. Now, I want to pause real quick, okay? When you are combining these, for instance, NH3, okay, you have N2, H2, actually 3H2, okay? I don't want you to get yourself fixated on the subscripts and coefficients when you are combining them, because you have to think about it in the way we did in chapter 2. When ionic compounds are formed, we have an ion of a cation and an ion of an anion, okay? They come together, single atoms, okay? You have to think of it that way. So again, if I have my N2, I'm just going to write this down and then we'll look at it. Okay, so I hit exit. Okay. Nope, then I'm going to go back up one. Go to the other camera here. Okay, so in order to have N2 and 3H2 yield 2NH3, okay, I can't focus on any numbers. Okay, all I want to focus on are the hydrogen and the nitrogen. Okay, hydrogen, again, is a +1. Nitrogen, because it's in the 5th group, it's going to have a -3 charge. When we these down here, we get NH3. So we get the product there. Okay. And you are able to do that because think of it this way. When you have a chemical reaction occur, imagine that everything on the reactant side is going to be broken apart. So these are all going to be individual by themselves for a split second. And they're going to reform. Well, they have to reform appropriately. And they're going to reform much like we saw here. We're going to have the single hydrogens and the single nitrogens coming together to form NH3. So we're going to have these come together to form two nitrate molecules coming as our product here. Okay, so it's very important you keep that in mind when you are looking and creating these types of equations. That is not tall enough. There we go. Back to the notes. And last example for a combination reaction, we have eventually that bar is going to disappear. We have C3H6 plus Br2, Brinkel off. They're going to yield C3H6Br2. It's a liquid, okay? But the underlying premise of these reactions is multiple reactants coming together to form a single product. Our second type is going to be the exact opposite. That is, we have a decomposition reaction. This is where we have a single substance or a single reactant that's going to break down into two or more substances. And these can be, not going to lie, somewhat complicated in the sense that depending on what is reacting in these situations, you might have some components that might form a gas to where it may kind of be like, oh, that, maybe added a third or fourth product here. But we'll worry about that later. Okay. So we have a single substance breaking down after something has happened. A lot of times it's heat or something else that it causes them to break down. For instance, look at the first example. Calcium carbonate, CaCO3, breaks down to calcium oxide and CO2. That's kind of the example that I was talking about where, it may not break down how you expect it to break down, okay? But we are still accounting for it. We still have one calcium on both sides of the yield sign. We have, we've got one carbon on both sides, and we have three oxygens. So everything's accounted for. It's just, you may have thought it breaking down into some other fashion. Second one, we have KClO3, so potassium chlorate, yields potassium chloride and three oxygens, okay? Lastly, hint, hint, this last and third example here is a very good one to know, okay? Here we have NaN3. You might think that's sodium nitride. Well, technically yes, but really the name is actually sodium azide, okay? Sodium azide breaks down into sodium and nitrogen. This type of reaction relates to the image, the picture that you see up in the top left. That is what used to be, I don't know if they still use it now, but for a long time, cars that had airbags in the steering wheel or anywhere else, drop my marker again, would use a decomposition reaction of sodium azide, where you'd have sodium azide present in the steering wheel. Whenever a crash would be detected, maybe like a addition of some electricity or heat that would cause the reaction to take place, where sodium azide would break down into sodium and nitrogen gas. The nitrogen gas that is released from this decomposition reaction is responsible for your airbag inflating. Now, again, that was an older method. Some may still use it, but I think they've kind of gone away from it because they found that sodium azide, some people might be susceptibles or not the word I want to say, but they may have had an allergy or even inhaled some of the chemical to where it was bad. In fact, some people didn't quite make it. Not because of the reaction, but because of their exposure. I think that's where I was looking for, to sodium azide. So I think they've kind of gone away from it. But for a long time, that's how airbags work, chemical reactions. All right, so let's talk about writing balanced equations for combination and decomposition reactions. So I'm just going to talk kind of briefly about the sample exercise here. And one thing I want to point out is you are not always going to be given the chemical formulas, okay? For instance, you're going to see situations to where you are given the names of the compounds and you have to come up with the chemical formulas. That is why I put such great emphasis on knowing the rules of naming and formula writing for compounds. Okay, there's no turning back now. Okay, so right now it says for A, write a balanced equation all the way at the very top for the combination reaction between lithium metal and fluorine gas. Okay, so if you see my little pointer here, you should be able to see that now. Okay, lithium is a solid and fluorine's already a gas. So Li and F2. Again, F2 because it's a Brinkelhoff. So here you'll see LiF2 yield. It's a combination reaction, LiF. Fluorine is a -1 charge. Lithium is a +1 charge. When you whoop them together, you get formula LiF. Once you've got that, you then have to balance it. Okay, like we did in the first section, you have to write out everything on the reactant side, write out everything on the product side, and then start your balancing there. As you see here, we put a coefficient of 2 in front of the lithium on the reactant side and a coefficient of 2 in front of the lithium fluoride, and we are done. Next, the decomposition reaction that occurs when solid barium carbonate is heated. You'll have two products that form, one being a solid and one being a gas. So again, solid barium carbonate. Okay, get the formula BaCO3. Barium is a +2, carbonate is a -2. So when you put them together, you get BaCO3. Yields. Okay, BaO, it's a solid, and CO2 gas. Okay, again, that's a little sticky of one, meaning it's kind of got a situation. But as you start noticing that anytime we have carbonates as a reactant, they break down, you're going to have the formation of CO2 and as the gas, and then the solid with the remaining oxygen attached to it. Okay, it is balanced. Okay, when you write everything out, it is balanced. It is good to go. Let's do a couple of practice ones, shall we? And so for A, we need to write a balanced equation for solid mercury 2 sulfide, decomposing into its component elements when heated. Okay, so let's start with A first. Okay, so we have, what was it, solid, you can't remember. We have solid mercury 2 sulfide decomposing into its components. All right, that's not what I want. Okay, so first of all, we need to figure out what the formula is going to be for solid mercury 2 sulfide. Okay, well, mercury 2, it's telling us that it's going to be the ion or the cation of 2+ because of the Roman numeral 2. Sulfur is always going to have a 2- charge. So when we whoop them, we simply have HGS. So HGS, again, I like to put the little blank here in case I have to put a coefficient out here, which is a solid, we are told it's a solid, yields the components. Mercury, which naturally found mercury is a liquid, so that's a capital L, or not capital, lowercase l. And sulfur, which is a solid naturally. Okay, so let's list what we have. We've got mercury, we've got sulfur on the reactant, and we have mercury and sulfur on the product, which is good. There's nothing that's jumping out at us that's not supposed to be there. We have 1 mercury, 1 sulfur on the reactant, 1 mercury, and 1 sulfur on the product. Do we have to do anything? No, we do not. Just by simply writing out the equation, we are done with A. No balancing needed, but we still have it appropriate in terms of what the reaction would look like. Okay, that's a decomposition reaction. For B, we are to write a balanced equation for aluminum metal combining with oxygen in the air. Okay, so we have aluminum. Oops, sorry, I'm going to rewrite this. Okay, we've got Can put my line there in case we have coefficient. Aluminum, metal, which is a solid, plus oxygen in the air. O2. Okay, O2 is what you put here. That's a gas. Okay, is going to yield. So what is aluminum and oxygen going to yield? So we have to go back to our ionic compound roots. Okay, aluminum has a 3+ charge. Oxygen is a 2- charge. You know how I don't care the fact that here we have a 2 subscript on here. I'm just looking at a single oxygen atom because this is all going to be broken apart and reformed when the reaction is occurring. So we're going to whoop them. And we're going to get the compound Al2O3, which is a solid. And we'll be able to distinguish when something's a solid or aqueous or liquid or gas at another chapter. Okay? So, using my chapter 2 rules, I formed my product and putting O2 in here because of Brinkelhoff. So, let's list. Okay? Aluminum and oxygen on the reactant, aluminum and oxygen on the product. Here I've just got 1 aluminum, I've got 2 oxygens. On my product side, I've got 2 aluminums and 3 oxygens. So, where do we want to start? Well, let's take a look at, let's look at aluminum oxide, okay? The product and aluminum, okay? So, aluminum on the product side has 2, and aluminum on the reactant side has 1. So, if I put a coefficient of 2 on the aluminum there, that gives me 2 here for aluminum on the reactant. So I'm even on both sides for aluminum. However, oxygen is not, okay? So again, oxygen has 2 on the reactant, 3 on the product. Got to figure out what the lowest common factor is, which is by now you should probably know is 6. So in order to get 6 on both sides, I put a coefficient of 3 on the O2 on the reactant side, and that gives me 6 oxygens on the reactant side and a coefficient of 2 on the product side, which now gives me 6 on the product side for oxygen. But I also changed the total amount of aluminum on the product side. So now I have 2 times 2, 4 aluminum on the product side, which means I now have to match that on the reactant side, and I have to have 4 aluminums there, a coefficient of 4 placed there. And so now that gives me 4 aluminums on the reactant. So I've got 4 aluminums on the left, 4 on the right, 6 oxygens on the left, 6 on the right. So place a coefficient of 4 in front of the aluminum, 3 in front of the O2, and 2 in front of the aluminum oxide. And that is how you balance a combination reaction. All right. Next, we're going to get into our third and final one for the day. And that is going to be combustion reaction. Now, in the first video for chapter 3, section 1, I described to you somewhat briefly what a combustion reaction was, and the fact that it is important that you know what a combustion reaction is, because whenever we have a combustion reaction, these types of reactions generally produce a flame, and they're pretty rapid, but they most often involve hydrocarbons reacting with oxygen in the air. And when we have hydrocarbons reacting with oxygen in the air, our products are always going to be carbon dioxide and H2O, both gases. Excuse me. An example of combustion reaction happens inside the engine of a car. You have hydrocarbon, which is your fuel, reacting with oxygen from the air, and it's going to release carbon dioxide and water vapor. Now, this time of year, when temperatures start to get cooler and you're driving, you might notice you might be behind a car to where you see what looks to be water basically dripping out of their tailpipe, their exhaust pipe of their vehicle. And you're not wrong. That's because when it's cold outside, the H2O, or the water vapor that is a result of this combustion reaction, as it is exiting or coming close to the exit of the muffler, it begins to condense because it's coming into contact with that cold air, and it condenses back into a liquid form, and it is leaving the tailpipe in its liquid state. So you don't see it that often or really at all in the summertime or the warm days, but when you get to colder months, you'll start noticing that. And that is all because of this type of reaction, because of hydrocarbons reacting with oxygen in the air, forming carbon dioxide and water vapor. So you see here the examples, we have various types of hydrocarbons. We have CH4, C3H8, both reacting with O2, both producing CO2 and H2O. So again, if we were to write a balanced equation for a reaction that occurs with methanol, which has a formula of CH3OH burned in air, okay, you'll get the products, knowing that it's a combustion reaction, you'll get the products of CO2 and H2O. Follow along with me here. So you write your methanol formula here, reacting with O2 in the air. Again, always producing CO2 and H2O. And then you simply just begin to balance it. And you'll notice that this is a little different. In this case, you'll have a situation where you have 3 halves of O2. Okay, so yes, 3 halves of O2. You're like, you can't have fractions of a compound. Okay, you can't have fractions of a compound. But really what that 3 halves is, it is kind of like a placeholder. So when you add the coefficient of 2 in front of the H2O, it balances the hydrogen but gives us 4 oxygens in the products, okay? Because there are only 3 oxygen atoms in the reactants, we're not satisfied, we're not finished. So by placing a 3 halves coefficient in front of the O2 to give 4 atoms in the reactants, okay, that gives us that. That's fine, but because we've got 3 halves, if we multiply by 3 halves by 2 and then add the 1, you get 4 oxygens. But you can't have it. You cannot have a fractional coefficient. So what happens is we can multiply this entire equation by a coefficient of 2. And when you do so, you place a coefficient of 2 here. It gets rid of that denominator, that fractional 3 halves, and puts a 3 here, a 2 in front of the CO2, and a 4 in front of the H2O. So you've placed coefficients in front of every single component of that equation. But you cannot reduce it or simplify it any further because you have the O2 with a coefficient of 3. So sometimes it takes a little trickery and some thinking outside of the box to help us solve for this. Or you can do it the long way and just constantly just go back and change your coefficients. You'll get there eventually. But if you think outside the box and put a 3 halves there temporarily, then you can do that. But you could get there without the use of the fraction, but this might take you a little longer. All right, so we are to write the balance equation for the reaction that occurs when ethanol, another hydrocarbon, oh no, this is stuff for later, okay? When ethanol burns in air. Okay, so yoink. So we have ethanol, which again is going to be C2. I'm going to dim this just a little bit. Okay, C2H5OH. It's a liquid. It's going to react with oxygen, which is a gas, and it's going to yield C2. Oh, sorry, it's a C2. CO2 gas. Oh, my goodness. Too close. CO2, I'll get it right, don't worry, plus H2O gas. Okay, let's list what we know. We've got carbon, we've got hydrogen, and we've got oxygen. Carbon, hydrogen, oxygen. All right, let's look at what we have so far. So here on the reactant side, I've got 2 carbons. Okay. Hydrogens, I've got 5 plus 1 is 6. And oxygen, I've got 2 plus 1 is 3. Over on the product side, I've got, again, checking all my products, I've got 1 carbon, 2 hydrogen, and 1, 2, 3 oxygen. Okay? So, again, let's figure where do we want to start? Okay? How about let's start simple. We have carbon. Okay? We have 2 carbons on the left, 1 carbon on the right. Let's put coefficient of 2 in front of the CO2. And before we go any further, let's change our numbers. So that gives us 2 carbons here. But now we have 4 oxygen plus 1. So 5 oxygens now. Okay. So next we need to figure out, what are we going to do now? Okay. What are we going to do now? We've got our carbons that are working okay. So we need a hydrogen and oxygen. So hydrogen is 6 over here and 2 over here. So if we put a coefficient of 3 there, that gives us 6 hydrogen on both sides. But now we've got 3 times 1 is 3 plus 2 or plus 4 is 7 oxygens. So we're not quite done yet. Carbons are good, hydrogens are good. Now we have to figure out oxygens. And so what do we have to do there? What we can do is if we add a coefficient of 3 here, that gives us 6 plus 1. And looky there, ta-da! We are all even on both sides. So that's taking what we learned in the first section, combining it with what we looked at in the second section, identifying reaction types to help us set up these chemical equations. Now, be on the lookout for worksheets dealing with reaction types here probably in the next day or so. So until then, if you have any questions, let me know. Be working on your problem set as well, the first 3 sections, because they will be due next week, most likely next Wednesday, the day of our super quiz. I'll talk to you a little more about that in one of our later videos this week. Until then, have a good one. Bye-bye.